Hi folks, welcome back to another lesson, and we're now going to move on from doing all those calculations and the electromagnetic spectrum to look at a specific phenomena of waves called diffraction of waves. So this one here, a bit more knowledge based rather than actual calculation based. So I'm afraid a lot of note taking in this lesson. So first of all, state the definition of diffraction, describe what happens in diffraction, and recognise and use diffraction of waves to explain, radio and TV reception. Okay, so first of all, waves travel in straight lines, okay? And that's just the way they work. So how can we get radio reception in towns and cities where there are lots of obstacles blocking the waves? And if even not in towns and cities, how can we get radio reception in rural areas where there might be a lot of trees or mountains and hills blocking access to a farm? Okay, so if you imagine this is a city, you can see all these tall buildings there. They would stop the waves if they're traveling in from, just for argument's sake, say this direction. But how is it that you could still get reception there? Now, you might say, well, what if we just put up more radio transmitters? And that is one way we get over it. However, there are other reasons that these waves can travel through to these other buildings on the far side. I'm going to look at that today. So the answer is simply diffraction. So I'd like to copy this down. Diffraction is the bending of waves around an object. Now you need to remember this, so make sure you put this in a wee sticky note or something. And it allows TV radio reception in hilly regions or crowded cities, because as you can see, there's my radio transmitter, and as the waves spread out, they start to bend. Okay, now there's not necessarily, you might think there's an obstacle there, but you can imagine this wee bit of the mountain there is the obstacle, and that's where it's bending around it to reach the hill that's inside this valley here. Okay, and you're going to learn why it is, in fact, that certain types of radio waves will bend more than the other ones, and this is why, for example, if you listen to certain radio stations, usually it's very hard to get FM stations, but if you switch to long wave, you've got a better chance of picking up those stations. And of course, we can replace the farm with these buildings in the cities. Okay, so again, I would like to write this down, folks. Longer waves will diffract or bend more than shorter waves. Now, I would like to try and use this word diffract because that's a technical term, okay? So longer waves will diffract more than shorter waves, or, because remember, wavelength and frequency are linked together, low frequency waves diffract more than high frequency waves. Okay, because remember, low frequency waves have long wavelengths and high frequency waves have short wavelengths. And you can see in my diagram here that the longer the wavelength, so remember, the wavelength is this gap between the waves here, so you're looking down on top of the waves. You can see as it passes this obstacle, there's more of a curve at the bottom end here. Whereas if the wavelength is very small, i.e. the frequency is very high, you can see there isn't as much bending or curving of the waves at the end there. So can you please copy these diagrams as well and make sure you get it as close as possible to the ones in the slide, because you are expected to be able to draw these diagrams, as you'll see later on. Okay, radio waves are longer than TV waves. Radio waves will bend more than TV waves around mountains. So if you live in a really rural area, the chances are is that you will be able to pick up a radio station much better than a TV station because the radio waves are longer waves. In particular, even within the radio stations, you'll probably have a much better chance of picking up a long wave radio station versus a short wave radio station or an FM station, because an FM station will have a very high frequency, i.e. a small wavelength, so they're not going to diffract as more. So before we had satellite communications, this was actually really, really important if you wanted to have decent radio reception. Okay, now here's the other type of diagram that you need to be able to draw. So if you make a copy of these diagrams as well, diffraction will also happen when a wave has to squeeze through a gap. So again, you can see a small wavelength, high frequency, the waves don't really bend this much, but for a big wavelength and a low frequency, you can see they bend much more. And one way I try and remember this is I say to myself, well, if they've got a big wavelength, so that means they've got a big wavelength here, it means there's more space for the waves to actually curve into, right? Whereas you can imagine for a short wavelength, there isn't the same amount of space for these waves to curve into. So that's how I remember that long wavelengths will diffract more than short wavelengths. And again, you may be expected to draw diagrams like these. Okay, so longer wavelengths will bend more than shorter wavelengths. Usually the gap is smaller than the wavelength. So what we mean by that is that this gap here, so this is the gap here, has to be smaller than the wavelength. And that makes sense because if the gap wasn't smaller than the wavelength, the waves wouldn't need to bend to get through it in the first place. One way to think about that is if you imagine you're trying to squeeze past somebody in the corridor, the smaller the gap you've got to squeeze through, the more you can have to bend your body to fit through that gap. Okay, and here are some real life examples of diffraction, or at least I hope they are, and I hope they're not Photoshop, but you can see here, you've got a gap here, and you can see these lovely kind of diffracted waves coming out. You can see here, this is probably like a natural harbour of some kind, and as the water goes through, you can see there's a lot of diffraction happening with the water waves. Okay, some examples of typical questions. Complete the diagram to show what happens to the radio waves as they are being given out by the transmitter and then passing through this mountain and into the farmyard. So a typical example would be a question like this. So the answer then is you would draw your waves in. So they kind of start off like this. Now I'm going to draw the waves as fairly big wavelengths. So when they hit the, now notice I'm trying to make these wavelengths the same distance apart because remember the wavelength doesn't really change. But as they get round the obstacle, then I start drawing them as curving quite a lot. And because they curve quite a lot, then the chances of them being picked up by the house will be bigger because you can imagine you could have an aerial sticking out the top here, and that would allow you to pick up your signal basically. So I would be confident in drawing this out. So maybe make a wee note of this diagram so you know exactly how to draw these wave diagrams, these diffraction diagrams. Okay, so let's look at a past paper question. Wave travels towards the entrance of a harbour as shown below. Complete the diagram to show the pattern of wave crest inside the harbour. So what does it look like on the inside this side of the harbour? So have a go at this one. If you're not sure, look at your notes. And here's the answer. So notice we've got the waves coming in, and then as they go through the harbour, you can see they bend at the edges. So diffraction of waves into shadow regions behind the wall. So first of all, we've got this diffraction here. Straight sections in middle and consistent wavelengths before and after the gap. So notice that we've kept the wavelength the same. Okay, but then we can see these wee curved bits at the edge to show that they are basically bending, they're diffracting. So that's to give you an example of what to expect in a past paper question.